Hello, everyone. This is Rashid Kibria from Fixed Research, University of Florida. In the previous demonstrations of RTL-FSMx, I have basically analyzed so many open source IP cores, and those IP cores had different types of complexity, sizes, and registers, and also they also vary in number of the modules they have, the design modules they contain. So in this demonstration, I have planned to analyze an SoC circuit. And this SoC circuit, I have basically built taking guidelines from the opencourse.org website. Now, this is based on OpenRISC1200 CPU core, which is a complex CPU core I have already analyzed using my RTL-FSMx and FSMs Ultra tool already. This SoC contains total 12 IPs. And here you see the ConMax. ConMax is basically the connectivity matrix that connects so many IPs in together. It is kind of some sort of bus protocol like AMBA or AXI, something like that. Open RISC 1200-based SoCs basically use this sort of bus architecture, and all the other it is still an IP itself, and the other IPs are also taken from opencourse.org website. So in total, it makes total 12 IPs present in this SoC, and you see here their interconnections, how they are interconnected with each other. The CPU core is connected to master ports. DMA core has some master port interconnections, and the other IPs are acting like slaves. So those are basically connected to the slave ports. And here, in total, this SoC has 159 RTL design files. Not only the module designs, it also includes the dependency files. That means those files which store some sort of parameter or local parameter type variables. In total, this SoC contains an RTL code which has over 180,000 plus lines of code, including the comments and everything. And so after I have also performed the logic synthesis of this SoC, it was really very time consuming and also so much complicated. And it shows an over 240K plus gates. Obviously, this is a very complex SoC, and in this demonstration, I will try to analyze this SoC circuit using RTL-FSMx and show you the results. So as the SoC has so many files here, 159 files, it actually takes time to be loaded. So I have already loaded all the files here, including the dependency files. There are total 11 dependency files here. You see these files are something underscore defines.v. It actually contains all the defined type variable files and registers. And after that, there are total 148 design module files. That means the main module, main design files, and those are shown here. That starts from this stuff and RTL design. And you see now there are total 148 files here. I have loaded all of them. I have also loaded the V2 version of the tool. And here you see after I can actually load this tool one more time. So I can go inside tools folder. Here I will see V2 and hit open. It will add this tool. And I can now hit the extract control efficiency button, and it will start running the tool automatically. It will just take a moment to get the tool loaded and begin execution or analyzing all the RTL design files to extract all the control efficiencies present in the SoC. So you see the process is going on, and it completed the whole process within only 7.4 seconds. This runtime actually varies depending on the system you use. So it is overall less than something like 5 seconds if I try to analyze it with this V1 version of the tool. And again, I can hit on open, select this thing, and it will start running the process. And here, yeah, you see, it is just taking like 5 seconds, something like that. So after that, we can now visualize the extracted state transition graphs, some of the STG files there. And you see this SoC has so many FSMs. And as a result, there are lots of output files being generated here. You can ignore the defined files here because those are actually kind of placed here because those are dependency files which are required for performing pre-processing and also pre-processing by the iVerilog tool. And that's why the all the dependency file needs to be put where the tool is being run. But the rest of the other files are actually the FSM files here. So just I will try to open this file, this FSM file. So it contains the finite state machine that is present in this ITC module, and it shows us the FSM extraction report, very similar to the FSM extraction report that design compiler produces. I have intentionally done this to keep it comparable with the industry grade standard tools so that it does not contain any other different meaning to other people. So here we see there are so many FSMs, and there are total 18 FSMs present in this RTL, and 14 states are unused, or you can call it as don't care states. And it is also showing us the FSM input signals, signals controlled by the state variable and the reset state. So now I will try to visualize the PNG file here. So I will click on this and hit open, and it will show us the FSM, the state transition graph of this module. And you can also find the STG report in more detailed format here. So you see all the file names have the same sort of convention. Just underscore FSM1 or underscore STG1, these things are happening. So it actually shows us the state transition graph in a text format, and also provides us why certain state transitions are happening. Let's try to open another FSM here. So here you see again the memory controller IP is also here. The same memory controller IP that I have already demonstrated. You can also find that here. Here is some UART module. Say I try to open this USB BF FSM. It is coming from the USB to design module. And if I hit open, it will show us the FSM there. And we can find out the associated state transition graph as well. So I will click on the PNG file, and it will show us the state transition graph here. Now, similarly, you can actually find here so many other FSM extraction reports. Actually, all the FSMs present in the entire SoC was extracted perfectly. That was a quick demonstration of RTL-FSMx on a complex SoC, that is our SoC, or which is built on the OpenRISC1200 CPU core. It demonstrates that RTL-FSMx is capable to analyze any SoC circuit within a few seconds. Thanks for hearing.